The name of the project is Channel Estimation in OFDM Systems. There are several current problems. The first one is carriers orthogonality is a constraint that can lead to a wrong operation of OFDM systems if not respected. The orthogonality is provided by IFFT, that's a numerical manipulation. An error of computation could change likely spacing between two consecutive carriers and break the orthogonality of the whole system. In this case, OFDM loses all its efficiency because the notion of orthogonality is an absolutely one. There are several exacting approaches. The first one is a block-type pilot channel estimation. And the performance of LS estimator is that the LS estimator minimizes the parameter without using any knowledge of the statistics of the channels. The LS estimators are calculated with very low complexity, but they suffer from a high mean square error. The performance of MMSE estimator is that this one can imply the second order statistics of the channel conditions to minimize the mean square error. The MMSE estimator yields much better performance than LS estimators, especially under the low SNR scenarios. A major drawback of the MMSE estimators is high computational complexity, especially if matrix inversions are needed each time and the data in exchanges. The performance of modified MMSE estimator is that this estimator are started widely to reduce complexity, such as optimal low-rank MMSE can reduce the complexity significantly at the expense of certain performance loss because it neglects the correlation points in different subsystems. And the LS estimator with 1D interpolation is also the channel estimator. The performance of linear interpolation is that the LI performance better than the piecewise constant interpolation. And the second order interpolation is called SOI. The performance of SOI is the SOI method performs better than the LI method, where the channel estimation as the data subcarrier is obtained by weighted linear combination of the three adjacent pilot estimates. And the low-pass interpolation estimator is that this can be performed by inserting zeros into the original sequence and then applying a low-pass finite length impulse response filter, which allows the original data to pass through unchanged. This method also interpolates such that the mean square error between the interpolated points and their ideal values is minimized. And the spline cube interpolation is called SCI. The SCI can produce a smooth and continuous polynomial fitted to given data points. And the performance of time domain interpolation is that it can have a high resolution interpolation based on zero padding and DFT. It first converts to time domain by IDFT and then interpolates the time domain sequence to n points with simple piecewise constant method. Finally, the DFT converts the interpolated time domain sequence back to the frequency domain. And the performance of PCMB estimator is that the LS estimator with 1D interpolation scheme is worse than the other two in terms of both MSE and SER. The performance of the PCMB estimator and ML estimator is almost the same, though the former performs slightly better in MSE at small SNRs. Conclusion: in OFDM system, efficient channel estimation schemes are essential for coherent detection of a received signal. After multi-carrier demodulation, the received signal is typically correlated in two dimensions, in time and frequency. By periodically inserting pilots in the time-frequency grid to satisfy the 2D sampling theorem, the channel response can be reconstructed by interpreting its correlation in time and frequency. Now I will introduce the MATLAB code. This is the main function. First, I initialize the variables such as nFFT, and I set the number of FFT is 2048, and the ng equals 5 times, and the number of OFDM equals 2560, and the number of SYM is 100. And the pilot spacing equals 4. This equation means that the number of pilots per OFDM symbol, and the number of BPS equals 4, and the number of SNR observations equals 11. Now I initialize the MSE arrays for different SNR observations as this part, and I initialize the 16 QAM as the modulation scheme. Then I pilot insertion in this part. First I assess the counter equals 0 and the array equals null. Then use a for loop to combine type arrangement. This I use IFT, means this inverse discrete Fourier transform, and then I add the cyclic prefix. And this equation is the cyclic prefix part to the appended. And this part is the channel code. I use the function from the MATLAB, such as the sigma Gaussian and gain Gaussian and the center frequency functions from MATLAB. And I set the maximum Doppler shift, and this equation equals this equation means that the sampling time and means the sampling frequency, and this part means a sign profile, specific properties to channel object. And this part I pass the OFDM signal through the created channel, and I use a channel covariance matrix for MSE estimation. This part is used to recept at the receiver end for various SNR range from 5 dB to 25 dB. I use for loop sets the range, and this part is serial to parallel conversion. and then I use FFT function to on Y. So I use I write a function about the channel estimation called LSC. There are 7 inputs. The first one is Y. This parameters means that frequency domain receives the signal, and this parameters means that pilot the signal, and this one means that pilot location. This one means the FFT size. This one means the pilot spacing, and this one is the mode. You can choose linear or spline. And the output is HLS. This means LS channel estimate. This part is LS estimator with linear interpreter. And this one is LS estimator with spline cubic interpreter. And this one is LS estimator with spline cubic interpreter. And these two is different because this part is DFT based, and this is not based on DFT. So I use the function about I use this function to estimate the MFSE. I write MFCE is as there. First, they have 7 inputs. The first one is Y. This means the frequency domain receives the signal, and this one means the pilot signal. This parameters means that pilot location, and this one means that the FFT size. This parameters means pilot spacing, and H means channel impulse response. SNR means signal to noise ratio, and the output is HMMSE. This means the MMSE channel estimate. And this part is MMSE estimator, and all of this based on DFT. So I draw 3 figures like that. The first one is LS between LS estimators. The right one means linear interpolation, and this one means the spline cubic interpolation, and this one means the LS spline cubic interpolation, but this one is based on DFT. And the figure 2 like that, this one. The right one means MMSE estimator, and this one, the blue one, is use the MMSE estimator, but this is different than red one because the blue one based on the DFT. And the figure 3 is this one. The blue one is LS estimator. This is the spline cubic interpolation, and the red one is LS estimator based on a linear interpolation. The green one is MMSE, the estimator. We can see the difference between the LS estimator and MMSE estimator. So the results like these 3 figures, we can see all of the features about between the MMSE estimators and the LS estimators. So all of this is my MATLAB code. So thank you everyone.